these statistics can be simple aggregate functions. For example, average, count, sum, standard deviation, percentiles on massive data sets. They can potentially contain filters, group bys, basically slicing and dicing this data across a number of dimensions. They can even have joins. They can have a nested query structure, anything that makes you derive value from this data. And last but not the least, they can actually contain some special functions, some special aggregate functions. They can be something like ML primitives, maybe k-means, or can be even something that you and I wrote in Java, a user-defined function. And ultimately, the goal of this is to perform some aggregate analysis on these massive data sets in order to derive some value out of this data. So before I actually deep dive into my talk, let me just give a brief intuition of what do we mean by processing these massive data sets interactively. So let's consider a simple query. And let's say that it tries to process 100 terabytes on data on 1,000 machines. Now, given current cluster computing framework, which operate on a disk, it takes around 30 minutes to 1 hour to process this data. And mostly this cost is involved in basically reading the data off the disk at a certain bandwidth. And then there might be certain communication costs, and then there might be certain I/O costs. If this entire process is now if this entire query is now executed on a framework that's optimized for in-memory computation, something like Spark, it still takes 1 to 5 minutes to process this amount of data. And again, memory brings down the bandwidth, brings down the time it takes to read this data off the disk. There is still communication cost. There is still certain processing costs. And moreover, this scale of data essentially warrants that reading even a few hundred gigabytes of data takes 10 seconds. Now, in this design space, what we are trying to essentially do is compute these answers within a matter of seconds. And if we want to do that, we cannot even afford to read this entire data online, as in when the query executes. So to this end, what we would like to propose is essentially execute these queries on samples of data. Now, what do I mean by query execution on samples? So let me illustrate it with a simple example. Let's say that we have a small table that reports the location and salaries of all the employees that work in a particular company. Now, if I want to ask a question as to what is the average salary of all the people that work in this company, one option is that I can always go to this table, read all the rows in this table, and give you an exact answer. Another possible strategy is that I can create a uniform sample of this table. A uniform sample essentially means that each row has an equal probability of being represented in the uniform sample. So in this case, let's say that we create a uniform sample with a probability of 1 by 4, and we get something like this. Now, what I can do is I can actually compute the average salary of the people from this table. And instead of the exact answer, I can get somewhat close answer. Now, it has to be noted that this answer in itself has very less value, because we do not know how far is this answer from the true answer. So in order to associate some value to this answer or to make this answer meaningful, what we require is some notion of an error bar with this answer, which can actually tell us as to where or how wide is these error bars and the answer as compared to the true answer. Another point that I would like to make here is that as you can always control the size of the samples that you would like to create from these tables. What this means is that you can actually sample with a higher probability. So in this case, this particular table is created with a sampling rate of 1 by 2, in which case you would probably get a more accurate answer with a smaller error bar. So the meta point that I would drive home is essentially sampling provides a smooth trade-off between execution time and the error that's incurred by this query. You can always get more and more accurate answers if you work on bigger and bigger samples. Traditional databases, or mostly all the query frameworks that we currently operate on, are at the far end of the spectrum. They essentially execute this entire query on the full data set and give an exact answer. However, there can be a number of applications which probably care both about latency as well as accuracy. So for example, if I want to find out the average RTT of a bunch of client applications that are suffering with an outage, what I would probably want is giving a fairly approximate answer, maybe like with the 99% accuracy in 5 seconds, than an exact answer in half an hour. So there can be other applications which are not so prone to this kind of like real-time analysis. But the key point here is that as the amount of data keeps on growing, there is some value in actually operating on a subset of the data and give an approximate answer that's good enough, rather than actually operating on the entire data and giving an exact answer. Another point to understand in these scenarios is that there can already be pre-existing noise in this database. There can be some error that's associated with the way that how the data is collected. I mean, we normally like have these data collected at certain intervals, and there can be this inherent error that's associated with this measurement strategy. So suddenly now it becomes a question of not being approximate versus exact answers, but rather where would you want to be on this curve? Because even if we operate on the entire data set, we are actually not getting an exact answer in the statistical sense. So what is BlinkDB? BlinkDB is a data analysis warehouse system that, first of all, builds on Shark and Spark, so it's kind of like compatible with the entire AmpLab stack. It returns fast and approximate answers with meaningful error bars by executing these queries on small samples of data. And furthermore, it's completely compatible with Apache Hive, and it supports Hive SQL-like query structure with just minor modifications. So all your Hive aggregate queries can actually be ported to BlinkDB, or essentially you can just use those queries for quick analysis with like very, very small modifications. So before I get into the rest of my talk, let me just give a brief intuition of what basically sampling enables. So here is a small query which basically tries to compute a percentile on a certain, on a few terabytes of data. On a few petabytes of data. And essentially what it tries to do is it tries to analyze this trade-off between response time of the query and the fraction of the data that it works on. So on the x-axis, we have the fraction of the data. 1 means that it's working on the full data. As we go towards the right, it basically means it's working on a 10% sample, a 1% sample, and so on and so forth. The y-axis is the query response time, as to how much time it takes to execute this query on these samples. Now, these numbers are not much of a surprise, because most of these queries are actually I/O bounded. So if you actually work on a 10% sample, it's highly likely that you essentially get a 10x better response time. What is really cool about it is that these are the errors that are associated with these sample of data. What this really means is that I can get an answer with 99.98% accuracy actually 10 times faster. And I can get an answer with almost 99% accuracy 100 times faster. And this is what sampling enables. It helps us make a smooth trade-off between the accuracy of the answer and the time it takes to compute this answer. And what it tries to do is it basically allows us to incur very less errors. I mean, these errors probably, depending on the use case, might not even be very relevant. And it basically gives us this extremely fast response times for the query. So as far as the BlinkDB architecture is concerned, we are built on Hive and Shark in some sense. So as Reynald talked about yesterday, the Hive architecture looks something like this, which is you have the HDFS layer at the bottom, then you have MapReduce on top of it, and then there are a bunch of meta stores, the SQL parser, query optimizer, physical plan generation, execution engine, and so on and so forth. Now what Shark does is it tries to replace the MapReduce engine with Spark. It makes changes to the query optimizer. It has a new physical plan generation strategy, an execution engine. And what BlinkDB does in this space is essentially to augment the functionality of Shark. So we do retain all the existing functionality. So there is nothing that you lose when you're trying out BlinkDB, because it's exactly built on Shark, and all it does is add some extra functionality. And in terms of extra functionality, what we really add is we add these approximate aggregate operators, sampling as a primitive kind of things, to base Shark. So you can expect something which is basically working hands in hand with Shark. You can actually get exact answers on your existing warehouse for some queries. And if you want to do a quick analysis, you can just create a sample, do a bunch of these things. You can probably get an error bar and get an idea of what the data looks like. So this is designed to work hand in hand. So let me give a brief, let me spend a couple of slides on what the BlinkDB alpha release looks like. So first of all, BlinkDB was released and is available at blinkdb.org. What it does, this alpha release, it allows you to create these random and stratified samples. Stratified samples are biased samples across a certain dimension or a set of dimensions, which may be useful for filter queries or group by queries, any kind of those queries. And it allows you to create these samples on any native table that might be in the store, warehouse, or any metallized views. And the most important thing that it enables, it basically adds these approximate aggregate functions to these data, to this query plan. Which means that now we can, instead of, if we want to compute the average, count, sum of these on these data sets, we can instead use approx sum, approx average, approx count on these small samples of data. And the goal here is that it would return an approximate answer with an error bar that's hopefully meaningful. So let me spend the next couple of slides talking about how does the syntax kind of like works out? How does it gel well with all the existing Hive warehouse or the Shark warehouse? So the first step in working on these samples of data essentially involves preparing this data. So in this particular query, or in this particular set of example, I would just show a log which might be potentially terabytes or petabytes in size, and you would just want to create a small sample to just derive some meaningful insights from this log. So the first step is exactly how you reference an external table in Hive. So there is nothing different about Hive or Shark in how you reference this table. All you do is you basically provide a table name, which is logs in this case. You provide a schema, and you provide a location on HDFS that stores that file. The second step, which essentially is an extension of the CTAS, or the create table as select syntax, allows the user to create a sample, which in this case is referred to as log sample. And it basically takes in a table or a metallized view or a subquery as the other argument, and allows us to add this sample with operator to this query. Now, the sample with operator can be just thought of as a random sampling operator, which in this case takes a probability and creates a 1% random sample from this particular table. Furthermore, since we are truly compatible with Shark, this exact sample that we created can be completely cached. So, as Renaud pointed out yesterday, there are two ways of caching these already existing tables in Shark. You can either append the keyword underscore cache to a particular table name, or you can actually use the table.cache property. Furthermore, now, when you are trying to analyze this data, BlinkDB requires you to set two flags. The first one is the size of the sample that you want to work on. And the second one is the size of the original data set from which this sample is created. Now, once this is done, BlinkDB allows you to basically execute aggregate queries over these samples. So what these aggregate queries are, it basically requires you to prepend this word called approx underscore to a well-defined aggregate in Hive. And the answer you will get would look something like this. So it would be a hopefully approximate count with a meaningful error bar at a certain confidence interval. So this confidence interval is a statistical quantity that says that, in colloquial terms, I'm 99% sure that this answer contains the true answer. Furthermore, there is actually a lot more to the alpha, in the sense that this sample with operator can be actually anywhere in the query graph. So you can essentially create a sample on any subquery. So it can be like a bunch of tables which are joined. It can be a bunch of tables which are filtered across a number of attributes, and so on and so forth. It also supports almost unmodified Hive queries on these samples. So the only modification, as I mentioned earlier, requires you to prefix approx underscore to an already existing aggregator. And you can always use the same group bias orders that normal queries contain. There is a small limitation in the alpha, though. The output, which is the answer and the error bar is currently basically outputted as a string. So this output of the query currently cannot be piped into another query. Also, the order by operators and these kind of operators will actually show you a lexicographic ordering rather than a numerical ordering. But this is something that we can easily fix by implementing this as a native data type, and this will be soon fixed in alpha 0.2. Looking ahead, there are a number of features which we are actively working on, and I would like to discuss some of these features that are coming up in the next couple of releases of BlinkDB. The first one, which is actually, which should be hopefully out like within a week or two, is that we will be integrating BlinkDB with Shark as an experimental feature. So if you download the latest release of Shark, you can just turn on a flag and enable BlinkDB on your warehouse. And being like completely compatible with Shark, you can just like create samples from your already existing tables. You can do any of those operations and derive value from these approximate queries. The second kind of like big work that's coming into this area is that we are trying to automate this sample management. So if you actually think about it, I mean, creating, deleting, managing samples should not be really exposed to the user. This is not something that the user should ideally worry about. When I'm a user, I just want to probably answer the query in whatever, with whatever accuracy, and probably whatever time I give it to. And similarly, I can prefix error bounds and things like that, and I'll be talking about it briefly in the next couple of slides. The next thing, obviously, is we would be supporting more and more Hive aggregates, and even user-defined functions, as I initially promised. These user-defined functions are something user-defined aggregate functions. These user-defined aggregate functions, or UDAFs, are something that are written in Java, for instance, or Scala. And what it means is that you can write a function, and BlinkDB would try to give an error bar associated with this answer if it tries to operate on a sample of data. Lastly, anything about like approximate query processing, I mean, there is always a caveat that the answer itself might not, or the error that we give with the answer might not always be true. So as an example, I mean, let's say that you want to calculate a max or a min on a sample of data. There is no way that you can give a statistically sound error bar on this, because your data can always have an outlier, and unless I reach that outlier, no subsample of this data can actually accurately estimate the max or min. So there are many functions in this category, and this problem is further important if you are talking about user-defined functions, because many functions can actually share characteristics of those functions. And it becomes important of some correctness test, which can actually tell me whether the error bar that I'm giving by whatever methods I'm calculating, whether it's sound or not. Because the last thing we would want to do is to actually mislead the user and give him a wrong error bar. And then there are further more kind of like plans in the pipeline, something to do with like a better scheduler in Spark that deals with approximate queries, as I mentioned, the primitive data types, and so on and so forth. So let me spend brief moments on what does each of these mean, and what are we doing about it. So first, the automatic sample management. As I mentioned, the goal of this strategy is to basically enable or abstract out the details of creating, deleting, and managing samples from the user. The interface we would like to provide to the user would just be a Hive query or a SQL query, and then allow the user to add a time bound to this query. Now, depending on this time bound, ideally the system should select an appropriately sized sample of data and return an approximate answer with an error bound. Now, if the user is not satisfied with this answer, she can always increase the time it takes to execute this query, in which case we would give a more accurate answer with a smaller error bar. And this all should happen under the hood, because all you want to do is you want to abstract out the details of how samples are created and maintained and read in the system. And another kind of like bringing in the kind of like a parallel argument, the user can always have an error bound to the query, in which case BlinkDB would like to give the fastest possible answer with that error. So just kind of like showing the overview of such a system, what would you have is basically when an original data comes into the system, the sampling module, first of all, creates a bunch of these random or maybe biased samples on these tables or materialized views into the system. And this could be created based on probably your query history, or some kind of like workload characteristics, what kind of queries have been asked in the past, and automatically these samples can actually be created in such a system. And furthermore, I would just basically add an optimality condition. A practical condition in this case is that most users would like to provide a storage budget to create these samples. I mean, we cannot actually have as many samples as we would like. So there should be some kind of optimality condition in these samples, or just have the best possible sample that could fit in that storage budget. Now, these samples can obviously be, some of these samples can be striped on disk, other samples can be cached in memory, and this entire thing should be automated as well. Now, when a query comes into the system, instead of actually operating directly on the sample, it should just have a time bound or an error bound, in which case, first of all, a query plan gets created, the sample selection module tries to select an appropriate sample and reads that part of the sample depending on the latency or the accuracy requirements of the query. And this, again, is a function of where this data is placed, how much data is to be read, the query characteristics, and the distribution of the data. And finally, based on this, we would like to create a new query plan under the hood, and then just return the corresponding answer as before by executing it like on the Shark and the Spark infrastructure, and return an approximate answer with an error bar. The next thing that we would like to immediately add is essentially support more and more aggregates and user-defined aggregate functions that people can write. To this end, we would like to leverage statistical techniques as Bootstrap to estimate the error. Now, while I'll not go into the details of how Bootstrap works, but just to give a brief intuition of how it's working under the hoods, let's say that this is a small query that likes to operate on a sample of data and gives a corresponding answer A. Now, if this is a UDF, I do not really know what this query looks like or what the characteristic of this query is. So Bootstrap, can be thought of as an operator that essentially replicates this query and makes it operate on repeated subsamples of this data. So you take resamples of the corresponding sample table and then execute each of these queries here. Now, I'll not go into the statistical details, but what it really requires us is to actually launch a bunch of these queries, typically 100 queries on this data, and get a range of answers. And what this does is, these range of answers tries to estimate what is the variance of this corresponding answer A, which in some sense is a measure of the error that's associated with that answer. Now, one of the important things here is that the placement of the Bootstrap operator in the query graph is very, very critical to the performance. The further we can push down this Bootstrap operator, it's first of all operating on less data, because it might be possible that there are certain filter attributes or filter operators which have filtered this data to a great deal. And then the remaining query is also shorter. So one of the key optimization strategies in this design space is that we would like to actually not operate on 100 other queries in order to estimate this answer. What we would rather operate on is a small subset of this data, and actually operating on small subqueries and getting this exact answer. And this is something that we are actively working on. However, there's a caveat, as I mentioned earlier, Bootstrap can fail. Bootstrap, as far as this is concerned, it does not make any kind of assumptions about what these queries are, and it is totally possible that Bootstrap can return a wrong error. To this end, we have been working on these kind of runtime correctness tests, which essentially tell you whether the corresponding error that has been returned by BlinkDB is sound or not. So the question that we are here asking is essentially, given a query, how do I really know if it can be approximated? And this should be done at runtime, because it depends, first of all, on the query that's asked. It's a property of the underlying data distribution and the sample on which the query tries to operate on. So all these things actually indicate whether a particular query can be approximated or not. And again, I'll not go into the details of the diagnostic test, but we have actually a good diagnostic test which can actually give us this indication of whether a particular query can be approximated or not. And what it tries to do, it basically tries to see whether the error actually improves as you work on very small samples of data and you keep on increasing these samples. And the way it computes this error is actually to compute this bootstrap on each of these very, very small samples of data. And again, like from a performance standpoint, it's actually executing 30,000 extremely, extremely tiny queries on these samples of data. And again, there are all these systems level challenges in like consolidating these tasks and actually executing this query very efficiently, because it's essentially the same query, and what you're doing is executing on these very, very small samples of data. And this essentially tells us at runtime as to whether this query can be approximated or not. Now, as I conclude my presentation, I would just like to point out that it's very easy to get started with BlinkDB. The alpha release is out, and it's available at blinkdb.org. It just takes 5 to 10 minutes to run this locally and or to spin an EC2 cluster, as is the case with every AmpLab software. We will be featuring the hands-on. We will be featuring BlinkDB in the hands-on exercises in a session just after this. And like Shark, it's essentially designed to be a drop-in tool. So you can have your existing Hive installations. You can even have your existing Shark installations. You can just drop in BlinkDB, point it to appropriate locations. It can even share the same metastore as Hive and Shark. So I mean, all your tables can now basically benefit from these operators. And more or less, I mean, essentially, in the future releases, we would be anyway integrating it as an experimental feature in Shark. So you don't even have to do this extra step of putting BlinkDB separately. To summarize, if there is one takeaway that I would like you to get from this talk, is that approximate queries are an important means to achieve interactivity in processing these massively large data sets. To summarize, BlinkDB, first of all, builds on Shark and Spark. It provides approximate answers with error bars by executing queries on small samples of data. And finally, it supports all the existing Hive queries with just minor modifications, just prefixing approx underscore to a bunch of these aggregation operators. Lastly, for more information regarding most of the behind-the-scene details, particularly automatic sample selection, the diagnosis test, please check out our Eurosys and KDD papers. With that, I conclude my talk. Thank you, and I'll take questions.
Hi. Two quick questions, if I may. First, any plans to deal with approximate distinct count, which is a very different problem than approximate count?
Absolutely.
And second question, or maybe an observation, building samples by rolling up other samples, is that practical? Is that statistically sound? Because it seems like a very similar issue to maintaining ordinary rolled-up aggregates and the.
Sorry, can you repeat the second question? Building samples by what?
In ordinary OLAP, you have a huge space of potential materialized views, and you solve this by creating, by doing roll-ups. You need to create fewer materialized views because you can roll up from existing ones.
Right.
Does that same approach apply here, or do you lose statistical soundness if you are creating samples based on samples?
I see. So regarding the second question, which is essentially talking about, how do we build these samples and whether samples on materialized views can actually be statistically sound? So the thing is that, regarding this sample with the operator, it actually depends on the property of the materialized view. So let's say that this materialized view is a join of these two tables. We cannot have a sample on a so let's say that there are a materialized views created with table T1 and T2. We cannot sample table T1 and sample table T2 and derive any statistical benefit by actually joining two sample tables. But we can always, let's say, for example, join two tables which are exact and then create a sample out of it. So what I mean to say is this is the case with BlinkDB's first release definitely, and this is probably the case if we do not have error propagation implemented at the core of the system, that you can only have one sample operator in the query graph. So if we are actually creating this bunch of materialized views, you can only sample this intermediate data at some point of the query graph. And then an aggregate operator is executed on that sample. And in that case, we can actually guarantee the statistical soundness and the corresponding scaling of that sample. What was the first question, please? Of course. So the approximate distinct count is a very good example of a query that actually does not work, and it is actually one of the queries that we feature in the hands-on exercises as well. The approximate distinct counts actually cannot be calculated using random samples. There are a lot of other kind of orthogonal work in database literature that creates this like special data structures to create these approximate distinct counts and things like that. But yes, I mean, random sampling is not good for approximate distinct counts. So this system is not like a one-size-fits-all. I mean, you cannot like execute all the queries in this design space. What we can do is we can have like all those aggregate queries, and I mean, a subset of those aggregate queries can actually be implemented.
You were showing some error rates. Were those p-values or false discovery rates you were showing?
The error rates, what are these values?
Yeah.
OK, so in the alpha, the error rates are essentially just values which are calculated by scaling the appropriate like standard deviation with like a corresponding factor. So I mean, it can be something like sigma. In case of average, this can be closed form error rates. So it's like 1.96, 2.54, depending on whatever confidence interval you're aiming at, multiplied by the corresponding closed form error rate, which is like in average, in case of average, it can be something like sigma by root n and things like that. In case of Bootstrap, the things that we are working on, the error rate is essentially indicated by the standard deviation or the variance of this underlying outputs. And all in all, I mean, the notion to understand this error rates is that we are trying to characterize the variance or how this answer can actually like be different if we operate on repeated subsamples of this data. So this is what the error is, which essentially is an error in practical sense.
Yeah, it's just people are used to false discovery rates. That's sort of a known quantity in
Sorry, can you please
false discovery rates. If you report those, I think people will have an easier time understanding what you're calculating.
Right, absolutely. And I mean, yeah.
Yes, I noticed you need to set the total size of original data. So is that required for the sampling? Because that total size might not be trivial to get it for dynamic data.
The total size is essentially, I mean, it's required for estimating some errors. So I mean, for example, if you want to estimate the error in sum or the count, you would probably want to scale it essentially to the appropriate thing. So first of all, it's required in the answer. If you're calculating a count on a sample, you would want to scale the corresponding thing to the actual value or to the estimated value. And second, the error correspondingly has to be scaled up. So this total size of the data is used for that scaling.
All right, 2 more questions.
I think my question is like, you are most likely assuming most of the distribution is Gaussian and calculating a confidence level.
Right.
So now, what prevents you from just calculating a prior distribution for, let's say, a column in a table and use like some kind of like Bayesian generative probability to generate the posterior probability. Mm-hmm. So that way, every time you may not have to scan the like column of a table many times, because so if you do that experiment, what difference will give like every time you scan and create a statistic, or just create a prior distribution once and just use as a generative thing to calculate average or count or I mean, just idea.
That's definitely like a good kind of like direction to think into. The kind of like the kind of disclaimer with like actually like assuming that a particular column would always have this prior distribution is that when you have more and more data into the system, or typically these queries actually operate on different data at different point of time, right? So when a new kind of data comes tomorrow, these subtle kind of like changes in prior distributions can actually result in like subtle changes in error. And as you saw, like, I mean, we are trying to actually characterize very small errors. I mean, if so, again, like it might be a good strategy to actually keep all these distributions of data and just use those distributions to characterize this error. What we would like to in turn do is essentially create samples of this data, which in some sense is again like a notion of this distribution of data, and then work on these samples. So when a new data comes in, you have a new sample, and what you do is you just execute that corresponding query on that sample. But I do agree that it's a valid approach as well.
All right, last question.
Hi, regarding the outer layers, I think it does not just apply to the non-aggregated functions like, max or min, right?
Right.
Even for aggregated functions, you still have that
Absolutely.
problem, right?
Absolutely.
Another-
And again, like, yeah, just to kind of like add to this thing, I mean, there is like an exercise that we have in the Wikipedia data count, like in the BlinkDB exercises. And I mean, there are page views, right, which are actually really, really skewed. And if you have those kind of distributions, if you just want to compute a simple aggregate, maybe like count or sum, I mean, it's totally possible that small samples can actually really miss those outliers. And the error bar is not sound enough, which is where the correctness test comes into.
And sometimes this distribution information could be predicated, right? Which makes the prediction very hard
Exactly.
to make.
Right,
from the
absolutely.
start
So
of the-
it is totally possible for the prediction to fail, but what the entire motive behind these correctness tests is that we would like to at least tell the user that the prediction failed. So BlinkDB would never return an answer that's wrong. I mean, we would never say that this kind of like approximate answer is 2000 plus minus 1000, and in which case like the 1000 has no kind of like statistical soundness. So this is what the runtime correctness test ensures.
Thanks. Let's thank
Thank you.
Samir again.